Okay. So probability spaces are used to build random variables. Like this. This is really all that or a probability distribution. This is what it is. So, similar to having a set of events, each of which have some probability of happening, where the probabilities, you add them up and they have to equal 1. Something has to happen. So, everything has to equal 1, but how you break down that 1 can be any way you like. So, in a random variable, it's the same thing except now it's a number. And this number will occur according to some probability function. And this number occurs at the same frequency which the elementary event that it's defined from occurs. That's a very long-winded way of saying that the probabilities don't change. The probability of events have a certain probability in A. All you're doing is you're now assigning a number to these events, and therefore those numbers happen at the same frequency as the events that they're based on. And all right. Okay, so to emphasize the fact that probability spaces are not numbers, we talked about a cube that was colors, not numbers, just colors. And we defined this probability space. From that probability space, for every possible event, we map it to some number. That mapping, you can picture it different ways we discussed last class. One common way is like this. This is a map of a probability distribution. All of these are talking about the same thing, okay? They're just different ways of thinking about it. So maybe one makes more sense to you. Maybe in some situations one is more useful than the other, but all of these are the same thing. So thinking about mapping events to numbers in a function kind of way, like in a programming way of thinking, it works like this. Thinking about it visually, about a set and as points each that have like a literal arrow coming out of them and hitting some point on the real number line. Sometimes viewing things as where they are on a line is useful to think about, or maybe it makes more sense. Also, you can take each of these numbers on the real number line and just put them as points on a graph as the x-axis. And then the y-axis, you make the probability function. So each of these points in the set happen with some probability. That is captured here in this type of graph as its vertical amount on this graph. And if you view this type of graph as taking something that had a size of 1, because probability spaces if this whole thing is a mass of 1, probability spaces chop this up into sort of blocks of area where here, because there's 6 outcomes, they all take up equal amounts of area. So if you chop this 1 up into 6 pieces, equal pieces, then for each piece you have 1/6 of the original one. Okay, so this way of thinking is going to be useful soon. This way of framing probability. So you have something with a mass of 1, and you want to spread out the mass somehow. Here, we're chopping it up into blocks, and each of those blocks have a certain size. That size that they have from the original block, that's their probability of occurring. Whatever number you want to assign to that block is up to you. So what's the point? I mean, like, why do any of this? The point is to have events that can happen that you can assign to numbers, so then you can calculate, so that you can make predictions. And one way of making a prediction is to figure out what the average is. And when you're talking about numbers, the idea of an average is very simple. When you're talking about other events, just whatever events you want, it's raining, I don't know, I like 70s movies, whatever, today's Tuesday. What's the average of those? Like, those are, they might be true statements, but there's no sense of what an average means. But with numbers, an average is very clear. So that's why we care about probability distributions. It's in order to use numbers and use probability theory together to be able to make predictions about numbers. One property that random values have is, random variables have, is an expected value, which is defined as the weighted sum of each of the possible outcomes multiplied by its probability of occurrence. So here you have the different number outcomes, and each of them are scaled by their probability of happening. This is the definition of expectation, which is just the average, also the mean. And in the case of rolling a die, you could say that on average, you will get the number 3.5. Let's see. I would like to pick on somebody to answer a question about this. For anybody who feels comfortable with this, like if this is an okay idea for you, if you get it, I want to ask you a question about gambling. Nobody. If nobody brings it up, I'll pick somebody at random. Ah, Mateo. Yeah. Do you have a mic?
Yep.
Great. Hey. So, you get why the expected value of a die roll of one die is 3.5.
Yes.
Could you just quickly explain how you get from one to the other?
So since you assigned, I mean, it's kind of written out right there, but
Mhm.
since you assign the numbers 1 through 6, um, you just have to multiply them each by 1/6 since they have an equal probability of occurring, and then
Mhm.
add them all together to get the expected probability, expected outcome.
Okay. Great. So, one question. This 3.5 number, like you can't get a 3.5 when you roll a die. So why is that the number that you expect to get? Or why is that the average number that you would get on a die that only has 1, 2, 3, 4, 5, and 6 on it?
I guess because like it's not a matter of like what number you get, the average, it's more just like a sum of the expected values. So it just happens to be 3.5, which is in between two of the values. But I mean, if you look at it, it makes sense because there's three numbers on one side and three numbers on the other side,
Mhm.
equidistant from 3.5.
Yes, that latter description is perfectly good. Yeah, that's right. What you were saying before that is mostly right, but that the fact that 3.5 is equidistant from the three numbers to the right of it and the three numbers to the left of it is a perfect description of what it means to be an expected value. Okay. Um, so uh, there is a game rolling dice. I wish I could remember the name of the game. Do you know? Like the game, people they roll two die. There's snake eyes, um, craps. That's what it is.
Okay.
Right. So craps is a game where uh, uh, I think you crap out if you roll a 7.
Yeah, that sounds right.
Yeah. If you roll snake eyes, that's two ones. Then you get a big payout. Also, if you roll, I think, an 11 of any kind. So that could be a 5 and a 6, or a 6 and a 5, or a. In fact, I think that's it. Yeah. then you also get a payout. Whatever. So for, in Vegas, they say that the house always wins. So for the game of craps, where if you roll a 7, you're out. If you roll 2 ones, you win big. If you roll an 11, you get something as well. In all other cases, you get nothing. Why is the game designed like that? Why is that the game?
Well, it has to be most likely that you'll roll a 7 out of those 3 outcomes.
Is it just those 3 outcomes? It's not 3 outcomes. I mean, you're rolling 2 die. There's 36 outcomes.
Right, but you said that any other outcome, like nothing happens, right? Like if it's not a 1, a 7, or an 11.
Yeah, in those cases, I guess you get to go again.
Okay. So I mean, it's because like to roll snake eyes is a 1/36 chance because you have to roll a 1 on each die. To roll a 7, you could get a 1 and a 6, a 2 and a 5, a 3 and a 4, and then like a 4 and a 3, a 5 and a 2, and a 6 and a 1. I think so. It's 6 possibilities, if I'm doing the math right. And then an 11 is 2 possibilities. So the odds are in the house's favor because you have 6 chances to get a 7, 2 to get an 11, and 1 to get a snake eyes.
Right. So the 7 here, though, it comes from the fact that, how do you know that the 7 is going to be the most common number? There's 2 ways you can get there. One is the way that you described. You can count all of the ways and add them up and then see which one's bigger than the other. But as an expected value of 1 die, it has an expected value of 3.5. So if you have the expected value of 2 die, that value is going to be 7. And so that's what you would expect to see with 2 die rolls. You would expect to see the number 7.
Yeah, that makes sense.
Yeah. Right. Okay. Let's see. Great. Okay. Well, yeah, that's it.
All right.
All right. Yeah. Thanks very much.
No problem.
No. Okay. So the expected value is a number. You can talk about the expected value of a random variable or the expected value of a probability distribution. It's the same thing. Yeah, we talked about turning probability spaces into, I don't know, games with payouts, as we just did now, but in a different way last time. And we also talked about the idea of something called variance. And both expectation and variance are 2 things that you should have a firm grasp on. You should understand them well, because things that are going to be coming up are going to be combining. So expectation combined with variance and considering both of them taken together. So far, the expectation is what we've reviewed. Now I'm talking about variance, and variance is just a different kind of expectation. It's the average, it's some kind of average of the distance of everything away from the average. So this is a pictorial way of thinking about it or representing this idea that you can have the same expectation, you can have the same average value, but the points that contribute to that average can be close to the average, in which case it's low variance, or they can kind of be far away from the average, which is high variance. So expectation, or the average value by itself, isn't so helpful. I mean, it's good. It's good to know what the mean is or what the average is, but knowing the average and the variance, you can have a better picture of what's going on. The equation is, this is the average, this is the distance from any point to the mean, to the line. So for each point, figure out how far away it is from the line, square it. The squaring it does a couple of things. First of all, it gets rid of any negatives. So this will always be a positive number. And also it kind of blows things up. It makes things bigger. So if the difference, if the point, if you look at this point here, I think I should draw. Take these 2 points, A and B. B, let's say it has a distance of 1 from the expected value. Then squaring that is still just the number 1, right? So if this distance is 1, then that squared is also 1. Let's say A, point A lies 3 away. 3 here. Distance 3, that's distance 1. A that lies 3 times away from the expected value, squaring it makes that a 9. So A gets sort of punished even more. He doesn't get punished by an amount of 3, he gets punished by an amount of 9. He gets squared punishment for being so far away from the line. That's the reason why, those are a couple of reasons why looking at squared distance is used here. And the variance is for every point, scoring it. For every point here, you give it a score of its distance from the line, and whatever that distance is, you square it, and taking the expectation is figuring out what the average is. So what's the average amount of spread, or the average amount of squared spread, or spread squared, about the line? Okay, before I go on, expectation and variance. Are there any questions about either of these? Because right now I'm just reviewing. After the break, we're going to be talking about a few different extensions or predictive methods using expectation and variance. So, right. Oh, yes. So another nice thing about the average number, this expectation, and again, the expectation is a number. You have it's the average, it's one kind of average of a random variable, is the expected value. A random variable is not a number. A random variable can be a number with a certain probability, but a random variable is not a number. Expectation is a number. So you can take a probabilistic object and you can turn it into a number. And that's its expected value. And this number has nice properties like scaling. It's invariant to multiplicative scaling. So you can multiply first and then do the average, or you can do the average first and then multiply it, and you'll get the same number, which is nice. Like that makes a lot of math easy. You can do things in kind of whatever order you want, and you'll get the same answer. And not only does it not matter if you multiply first and then take the expectation after, it also doesn't matter if you add. Do you add first and then take the expectation? Or do you take the expectation first and then add? With expectation, both of them work. Either way, whatever way you want, same answer. So these are two properties of the expected value. You can multiply and or you can scale something by a multiplier, or you can add things together, and it doesn't matter what order you do them in, or you can change up the order. If you don't know one, flip it into the other, and then if that's easier, great, do that. So these two things, being able to scale, like multiplying everything by 10, or adding, like playing a game with one payout and then moving on to a different game with a different payout, you can figure out what your payout is individually at each of those games and add them, or you can figure out what the payoffs would be for the combined event of getting a payout in each for all possibilities and what those probabilities would be, and it's the same number. Anything that has these two properties is called a linear operator. That means that it works like a line. in some sense. You can scale multiplicatively, and you can add, and the order doesn't matter. You get the same thing. This is the last thing I'll talk about before a break, which is this idea of a linear operator. The reason why we talk about this is because what we're building up to in this class is linear regression. And so what does linear mean and what is regression? That's what we're building up to. And up to this point, we're coming to here. What does the linear part of this mean? That's really why for this class we care about what a linear operator is. Yeah, linear operators are also good because they are easy to work with. And what I mean by that is I think I might be missing an E somewhere there. Multiplicatively. All right. All right. So the linear operator, or a linear operator, it's a very nice thing to work with because it can scale with multiplication, and addition can happen in whatever order you want. One example is changing currency. For this, I would like any student who is from, well, let's see. Yeah, any student who's from a foreign country or who's been to a foreign country. Currency exchange is a linear operator. So I'm just going to ask very obvious questions, and we're just going to show that that's a linear operator. Okay, how about Eating? Do you have a microphone?
Hi.
Hey. So I'm just going to ask you some simple questions, I hope.
Mm-hmm.
You are from China.
Yeah.
And in China, the currency that they use is called the renminbi or the RMB. So that's the currency in China, and the currency in the U.S. I'll just call it the dollar. If you have 1,000 renminbi, about how many US dollars do you have?
About about $142.
$142. Okay. Is that much really? Okay. Okay, and if you have $100, how many renminbi do you have?
7,000 about.
About 7,000. Great. Okay, so this is the way that currency works, right? If you're coming from China with 1,000 renminbi in your pocket, you can turn it into, in the United States, $142. Or if you have a $100 bill in your pocket in America and you go to China, I'm sorry, that should be 700. Then you can get about 700 renminbi. Great. Now, what I want to show is that in this case, each of these are true. To show that one is true,
Yeah.
if I have 10,000 renminbi, how much is that in US dollars?
420.
Yeah. So this is what multiplicative scaling means. You could first take you can take the whole thing and calculate the transfer rate by itself, or you can add up each of the individual pieces. Let's see. I'm saying something that's very simple. I don't want to confuse things. I'll just keep it like this. That shows number one. Okay, for number two, you can add in any order. All right. Okay, so Yiting, if you and me were coming in from China and I have 1,000 renminbi and you have 700 renminbi, and we're going to be combining our renminbi together, then we would have 1,700 renminbi. With this 1,700 renminbi, if we wanted to turn this into USD, how much would that be?
$242.
All right, 242. And where did you get 242 from?
From the 1,700 RMB.
Yep. So you did 142 plus 100?
Yeah.
Right. Great. Great. Then another way I could have done it is if I had, let me put this in a different color. If I had a bigger chart here, then I could just say what the scaling factor is. So the scaling factor is about 1/7. Actually, forget this. So 700 renminbi into US dollars if you want to go from renminbi into US dollars, you can just divide by 7. So another way that you could arrive at this number is to take 1700 divided by 7, and you should get something close to 242. Agree? Is there anything wrong with that?
No.
No. So now, instead of adding things, which is what you did before you added the number 142 plus 100, because that was the easy thing to do. Now, if I have 7,000 renminbi, how many US dollars do I have?
1,000.
1,000. Okay. Okay. So here you're taking some number of renminbi and you're turning it into dollars. You can think about it like adding them together after you've converted, or you can think about adding them together and then scaling them. So this is what this means. Therefore, like exchanging currency, this is a linear operator. It's something that you, and anybody who's dealt with currency exchange already understands sort of what it means to be a linear operator. The fact that you can multiply by a certain number, and it doesn't matter if you do it beforehand or afterwards, or if you're combining funds. Do you convert the pieces individually first and then add them together? Or do you add them together first and then convert them? There's no difference. Yeah.
Because it's more convenient.
Yeah, it depends on what's more convenient, but they both work, right? Like you'll get the same amount of money either way. Right? Or okay, if I send you with 1,000 renminbi to the bank and bring back US dollars, and then I send you out a second time to get 1,000 renminbi with 1,000 renminbi to get US dollars. How many US dollars would I have?
284.
Yeah. Now, so that is converting each of the pieces and then adding them together afterwards. If I add them together first, and so now I give you 2,000 renminbi, and you go and exchange it at the bank, how many US dollars do you have?
142.
I give you 2,000 renminbi. You come back with $142?
284.
284. Good job. Yeah. So this is what it means. Like that's what a linear operator is. Like, do I send you 2 times? Or do I send you once with twice the amount? It shouldn't matter. I should get the same number of dollars back. So not everything works that way. Linear operators do. Like expected values work in exactly the same way. Okay, great. Thank you, E2.
Thank you.
Okay, so this is about everything that I want to say. Yeah, we We touched on what it means to be a linear operator with expectation, also variance. I would like to take maybe a 15-minute break now, and afterwards we will talk about how to combine expectation and variance to do useful things. So, all right, let's take a 15-minute break. Thanks, everybody. All right, it's on pause now. So, yeah, do you guys like this idea of thinking about probability in terms of making bets and how much money you could expect to see making bets? That's a very good, consistent way to think about probability. Yes. Okay. Okay. I'll try to talk about things a little bit more in terms of money. If you have a particular example that you are thinking about, bring it up and we'll see what we can do with it. That's the best way to understand stuff. So, about this. Getting a heads. So now I'm playing a game. The game is there's a coin that's being flipped. Every time I'll call heads. And if I call heads, it pays me $1. If it's tails, I get nothing. So now I want to try to see what could I expect as far as earnings for different scenarios. Right. Let me pick on somebody. How about Andrew? Do you have a mic? Oh, you do not, but example. Okay, so sorry, that's right. Okay, so here, just about, oh, baseball player needs to swing. Oh, okay. Oh, you have an example. Let me jot it down. Baseball player needs to swing. Very good. Okay, yes, so Andrew, this is an example that we can work with. This would be making a bet on a baseball game. And I'm betting that a baseball player is gonna be swinging 10 times in the game, and if he hits the ball 7 out of the 10 times that he tries to hit the ball, then I win. I'm assuming it's also true if I get if the guy gets 8 or 9 or all 10 hits. So at least, I guess. Well, I don't know. I should ask Andrew, this is your example. At least. Okay. It wouldn't have to be at least. I mean, you could go for the exact thing, you know, it's just a different game. Fine. And so then, Andrew, I'll ask you two questions. In order to solve this, you need to know, which is, I guess, what's the payout on winning, and the penalty on loss. So how much can you win playing the game? How much would you lose if you lose the game? And the second thing is, yeah, so this game also needs to know how good is the baseball player at hitting balls. I mean, if he's, you know, really good, then maybe I shouldn't earn so much money. But if he's like the worst player on the team and that guy gets 7 out of 10 hits, then maybe that's a big payout. So I need to know what the payout is, and what you could lose on this game, and what's the probability that the player actually hits the ball any one given time. Given those things, you can solve all of this. Great. Okay, that is an example that we can work with. So this is a game. We will analyze this in a moment. Thank you for the example. I want to go back to what I was talking to before, but we can follow up with this. But you have all of the pieces here. So there's going to be 10 swings. This baseball player is expected to hit 6 out of the 10. Or on any particular time he swings, he has a 60% chance of hitting the ball. And the payouts are like this. So you could win or lose the same amount. But the number of ways that you win are fewer than the number of ways you can lose. So in some sense, it seems like if you look at answer 1, this seems like a bad bet for the winner, because there's more ways to lose than there is to win, and the payout is the same. So if he plays this over and over and over and over, that's not a very good way to make money. But question 2, the probability of the guy actually hitting the ball is better than a coin toss. So does the player being better than a coin toss, hitting a ball any one time, make it worth it to play this game? Yeah, is that enough? Is the player good enough to overcome the ways that he could lose to, yeah, win more often than not? All right, that is an excellent example. For right now, I'll leave it. I'll let you think about it. Actually, Andrew, if you can come up with this answer, that would be something. Question. Should you play this game to make money? Yeah, Andrew, this is a really, really good example. I will leave that to you to think about for a little bit, and we will come back to it. Yeah, I really like that example. In the meantime, I want to go back up, and I want you to spend some time thinking about a random variable or a probability distribution as like taking a chunk of clay that weighs a pound, and you distribute the clay however you want on a surface. So here, this is the surface that you're dispensing the 1 pound of clay that you have. And where you put it on the surface is going to be on some number. So these are numbers. That's the real number line. And then this is the probability. Let me pick on Royston. Do you have a mic? Okay, how about Vincent?
Yeah.
Hey, so I just want to know here, where I'm highlighting in green, do you see that?
Yeah.
Yeah, the x-axis here. What numbers should I put there?
This is with the coin flip, right? Like getting a heads on 3 times out of 10 flips.
Yes.
Yeah. So put I think 1 through 1 through 10.
Yeah, is that it? You're missing one.
I'm not sure.
Imagine you're either very, 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 very lucky, or otherwise you're very, 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 very unlucky. What is the 10 here?
Be the 10 times you flip it.
10 times I flip it, and what happens on each of those 10 times?
You're either gonna get a heads or tails.
Okay, for this number 10, is that 10 heads or 10 tails?
Um.
It can be whatever you want.
Okay. Yeah. I would probably say 10 heads.
Okay, 10 heads. So if you're betting heads and you get it 10 times in 10 flips, that's like the best of luck. What would happen in the worst of luck?
You get all tails.
Okay, what number is all tails?
That could be 1.
One is 0 tails. One is no tails.
Oh, yeah, it would be 0.
There you go. All right. Perfect. All right. Yes. Right. So there is actually 11 outcomes because you can get, all heads and all tails and everything in between. Okay. Great. That is it. Thank you so much, Vincent. I'm going to let somebody else know. Okay. How about Brian?
Hello.
Hey.
Hi.
Okay. So we're trying to fill out what this probability distribution is going to look like. So we have the x-axis, and the y-axis is going to go from 0 to 1 because it's a probability. Let's see. Do you have any feeling for what this graph might look like?
Well, I don't really know like the math behind it, but I would guess that like flipping heads 5 times would probably be like 0.5 on the y-axis.
Okay, is that it?
I would probably guess that it would look kind of like a bell curve, with like 0 and 10 being the least likely.
Okay,
I don't know what the actual numbers would be though.
sure. Let me get the picture down first, anyway.
Yeah.
And when you say bell curve, I assume that you mean that it would be symmetric as well.
Yeah.
Okay, I don't know. I try to keep it symmetric. Symmetric meaning that these two are the same size, these two are the same size, these two are the same size, whatever. All right. So something like that. You think maybe that's 0.5, but there's you're not totally sure. Oh, sorry about that. Okay. So you're not really sure what numbers to put here.
Mm-hmm.
You're not sure if that's 0.5 or what. Okay. Question mark then.
Yeah. I have no reasoning behind it. It's just kind of like intuition.
Yeah. It's a good intuition. So let me go down a little bit. Out of all of these possibilities, which do you think would be easier to calculate? Like the probability of all heads, all tails, half heads, half tails, somewhere in between, 4 heads, 3 tails?
Probably half and half, like probably 5 heads, 5 tails.
All right. Over here, this is x. That's x. So the probability that x is equal to 5, you think would be the easiest to calculate?
Either that or one of the extremes, like 0 or 10.
All right. Do you like one more than the other, 0 or 10?
0.
0. All right. So let's start with this left one. how would you think about calculating the probability of getting 5 heads out of 10 flips?
Could you multiply 0.5 5 times maybe? Because if you're flipping it, I don't know.
All right. Okay. And so what would this number be?
It would be 0.25. No, it wouldn't. I don't know.
No. I don't mean like if you put it into a calculator, what would you get? I mean, what does the number represent? Like, why is it 0.5 times 0.5 times 0.5? You say that the 0.5 is the
0.5 is like the probability of flipping heads on each individual coin flip.
All right, whatever. And on and on and on. Let's go to the one on the right. How would you think about that?
Maybe multiplying 0.5 10 times.
0.5 10 times. All right.
I don't know. I'm just picking, like, you obviously can't multiply 0.5 0 times because that would be 0. So I'd pick the other extreme. If that makes sense.
Yeah. All right. So maybe we shouldn't switch from the left so quickly. By the way, just to let you know, this way on the right is much, much easier. The way on the left is not so much fun. Well, it's fine, but it needs more stuff. But just to give you a sense for it, with this number, you said that the probability that x equals 5 might be equal to this, right?
Mm-hmm.
You said 0.25. What is 0.25? Where did you get that from?
That I just did the math wrong. I don't know.
Well, if you multiply 0.5 times 0.5,
Right. Yeah.
you can get 0.25.
Right.
Right?
Mm-hmm.
So what happens if you multiply 0.25 times 0.5?
You get
Getting
like the answer.
No, like what would the number be? 0.125.
Oh, yeah. Okay.
Yeah. All right. And then if you multiply this again, so now by 0.5 and by 0.5, then you got to multiply each of these by 0.5 to get the final thing. So, I don't even have to finish this, but so far, am I following the math here anyway? 0.5 times 0.5 times 0.5 times 0.5 times 0.5. You can calculate that by 0.5 times 0.5. That's 0.25. So that's now we're down to a fourth already.
Mm-hmm.
And then we're going to go down to an eighth, and then a 16th. Or as a decimal point, I've written it down here. And you say that this is the most likely outcome? Does something that happens like 7% of the time? Do you think that this number is 7?
Well, I wouldn't really know how to calculate it. Obviously,
Yeah.
it's wrong, but that was just my initial feeling, which
Fine.
is not right, obviously.
No, it's good. Yeah. Part of what I'm saying is like, it's good to have guesses, but there's sometimes ways that you can, maybe your guess is right, to like work through it, and then if you find something that doesn't feel right, then you can think about a different guess. In any case, for reasons that I wouldn't expect you to know, let me get rid of all this. This is a bad choice. This is harder than you think, and so let's not start here. I'm just showing you a way to like work through guesses and stuff, which I think is really good practice. So I will come back to how we'll come back to this. Okay, so this one is easier. And without thinking of your original approach, if I wanted to calculate, okay, if I flip a coin one time, what's the probability of heads?
0.5.
0.5. Okay, if I flip a coin 2 times, what's the probability of getting 2 heads?
0.25.
0.5. Okay, and where are you getting the 0.25?
Well, there's 4 possible outcomes, and flipping heads twice is one of the 4.
Yeah. Okay, this works. Okay. All that I'm writing down here on the bottom is just extra stuff. So the probability of the joint event of getting 2 heads in a row is equal to the probability of getting a heads on the first times the conditional probability of getting a heads on the second flip, given that the first flip was heads. All right. So if the probability of getting a heads on one flip is half of 2 straight heads on 2 flips is 1/4, then what's the probability that you get 3 heads?
Times another 0.5, be 0.125.
Okay. And then this is just going to go on. Okay. So how about 10 heads?
It would just be 0.5 times to the power of 10. Like, yeah.
Great. Is that a big number or a small number?
It's a really small number.
It's a really small number. Yeah. So this is, so far, we've gotten that far. Like we've gotten at least these bars, right? The 0 and the 10. So that's a good place to start. It's some really, really small number. Yeah, let's do it for 1 head. and then we'll take a break, and then I'll finish it up. But thank you for being patient, Brian. And also, I haven't forgotten about this example. It's a really good one. Or after a break, if anybody has thoughts on if you should play this game or not, that's really good practice. Ooh. All right. All right, how about the probability that x equals 1? So that you just get one head. If you flip one coin, and what's the probability of getting one head?
0.5.
0.5. Okay. One flip is 0.5. Okay, how about two flips? What's the probability of getting one head on two flips?
Like on both of them?
Nope. One head. This is
Oh,
x
one.
equal 1. No. I can do a fair coin. You flip the fair coin 2 times. What's the probability that you get exactly one head?
Would it be 0.25? No, 0.5. It would be 0.5. Never mind.
Oh, now you feel confident.
Yeah,
Why are you so confident that it's
because
0.5?
I thought through the possibilities, the probability space.
And so what are the possibilities?
Heads, 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 tails, tails, heads, tails, tails,
Mm-hmm.
and half of them have one head.
Yeah. So they all have a probability of 1/4. You're eliminating 2 of them. And so you're just counting this. Yep, okay. So how about 3 flips? This one's hard, I'll warn you. But your thinking is right. If you use that same thinking, you'll come up with at least a process for it.
Would it be 1/3?
1/3. Huh. Let's try it out. So, where does the 1/3 come from?
Well, there's 9 possibilities.
What are the 9 possibilities?
Heads, 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 tails, heads, tails, heads, tails, heads, heads,
Mm-hmm.
tails, tails, heads, tails, heads, tails, heads, tails, 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 tails.
That's 8. Let's see. I see heads, 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 tails. No, there is no heads. Oh yeah, heads, heads, tails. Heads, tails, heads. Yes, heads, tails, 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 heads, heads, tails, heads. Tails.
I think it's. Oh, never mind.
Tails, tails, heads, tails, tails, tails. I won't let you bang your head against the wall. There is no ninth. There's only 8 possibilities. There's 2 possibilities on the first, 2 possibilities on the second, 2 possibilities on the third. That's 2 times 2 times 2, which is 8 possibilities. So, yeah, you're gonna have a bad time if you're trying to think of the number. So yeah, okay. An easy way to go through this is to think about it like a counting in binary. If you know, do you know counting in binary? Like what I'm writing here? Let me hold on. Counting in binary. Do you know how to count in binary?
Sort of. If you give me enough time, I can do it.
Okay, what's the next number here? So this is 0, then 1, 2, 3.
100.
Yep. All right. And then?
101.
Yep. Then?
110.
Perfect. All right. And?
111.
All right. Anything else?
Then it would be 1000.
Yeah, right. If I wanted to keep this going, then yeah. Very good. So here, I will say, think of a 0 as being a heads and a 1 as being a tails. So in 3 flips, this is 3 flips. That's why there's only 8. Each time, this on the left maybe is the first flip, the second one is the second flip, the third one is the third flip, and it's a binary choice. I mean, it's only going to be a 0 or a 1, or a heads or a tails. So that's where the 8 comes from. Okay, so then given that space, what is the probability, do you think?
3 out of 8.
3 out of 8. Okay, why 3 out of 8?
Because there's 8 total possibilities, and 3 of them have 1 heads.
All right. And each of these have a probability of 1/3, you say? Right.
No, 1/8.
1/8, yes, 1/8. Thank you. Excellent. Okay. All right. So okay, just to get a shortcut, so that we can take a break. I'll try to lead you. I'm like leading the witness here. So for one flip, there's one way to get a heads. One way to get a heads. For 2 coin flips, there's 2 ways to get a heads. For 3 coin flips, there's 3 ways to get 1 heads out of all the flips. Yeah, so what do you think it would be for 10 flips? How many ways do you think there would be to get 10 flips?
10.
10 ways. Okay. So if 10 is going to be on the top, then what number would be on the bottom? I'll write it down for you, and then maybe you can tell me why it is that way. 2 to the 10.
Oh yeah, right, yeah.
Yeah, why is
I was
that?
trying to
Why-
come up with the actual number.
Oh, yeah, 1024, but whatever.
Okay.
Yeah. It's in this case, it's better to think about it in terms of 2 to
Yeah.
some power. Yeah, it makes things simpler in your head. But why 2 to the 10? Where is that coming from?
Well, because you're doing it 10 times, so we just, for 3 flips, you did 2 times 2 times 2. So then 4 flips would be 2 to the 4th power. So 10 flips would be 2 to the 10th power.
Very good. So you're noticing that this is actually 2 to the 3. So that 8, it's not any 8. I mean, you're right. Like, yes, there are 8 things here, and that's where you originally came up with the 8. But now you're looking at it a different way. This 8 is actually 2 cubed. It's that 8. And so therefore, you can understand where, like, the denominator is an exponent. Very good. Excellent. Yes. So now we have 2 of these numbers. We have it for 4. We have it for 0 and 10, 1 and 9. You might have noticed that this way is a little bit harder than with x equals 0. We're getting different numbers here. X equals 0, it's always the same number. X equals 1, the numbers change. X equals 5 is the worst one, which is why we'll come back to the. Let's do that after our break. Let's take like a 15-minute break. All right. Thanks, everybody. Just wanted to take a few minutes to draw out this sort of picture of the big picture, sort of where we're at and where we're going and why we're doing this. We've talked about probability spaces, and this is really necessary to understand what probability is and how to work with it, what the rules are. Then we expand this into random variables. So this is just taking a probability space and assigning events to numbers. So here's a probability space, and all these green arrows coming out of it, going to the real number line, is just some function that maps events to numbers. This is nice because you can get the expectation and the variance. Why we're discussing this is because we're building up to the idea of fitting a line that's best fit, a best fit line. So not any line, but like a line that is the best line according to something. And that something here is the best line is the one that minimizes the variance of the points around it. That's the way you calculate this line. And so that's why we're going through all of this stuff. And this is pretty much the course. Yeah, there's some stuff probably starting next week that I'll start to introduce some code. First, just realizing probability spaces and random variables in Python. Yeah, I guess I'll try to give some work before the end of this session of doing linear regression via code, because I heard that people wanted to do that. But in any case, so now you know where we're coming from. We're kind of done with probability for the most part. Now we're discussing random variables, expectation, and variance. And we're going to be stuck in here for the rest of today. And maybe including sometime this week, our next class. But then we'll be moving on to the linear regression part in code. Okay. All of that being said, before I go back to where we were, which I want to do this example because this example seems really nice. Let me give it even more space. So I want to do this example. This is a good one. I hope that you guys are thinking about it, or hopefully have a solution. But before that, I want to talk about this idea of probability distributions. And the reason why I focus on imagining this as a mass of 1 is, again, partly because, I mean, it works. It's consistent with all of the rules of probability and random variables. But the other thing is that right now we're talking about discrete distributions. And those are ones that look like bar graphs. I mean, any kind of bar graph you want. So long the area adds up to 1. That's a discrete distribution. What we need to talk about are continuous distributions. And that's things like this. So here, discrete distributions are like a bar chart. Continuous distributions are like smooth lumps. And you need a little bit of calculus for this part. But if you understand these things very well, the bar graphs, then really the transition to continuous, it's not that big of a jump. I mean, they're pretty close. So right now I'm trying to expand your way of thinking about these discrete distributions. In particular, that they can look very, very different. So we're seeing that a little bit here. Oftentimes people like to think about what are called uniform distributions. That's where all of the pieces of clay are the same mass, as in the case with a fair coin or a fair die. But there's other distributions, like counting the number of heads that you get flipping a coin 10 times. And that distribution looks different. There's a lot of mass in the middle, and less mass as you get far away from the mean. Yeah. All right. So right. So I said that we would come back to this, the probability that x equals 5. Let me get rid of this because it's just sort of a motivation. All right. Let me try to write this with words first. So the probability that x equals 1 is the probability of getting all tails. And this is 1/2, where this is the size of the success over the size of all possibilities. These are sets. So flipping a coin 10 times, oh, I'm sorry, 1 over 2 to the 10th, as we calculated. So the probability of getting all tails is 1 over 2 to the 10th, as we calculated here, 0.5 to the 10. I'm deciding to write it like this, 1 over 2 to the 10th. So I'm right, instead of 0.5, I'm writing 1/2. Right, and the way that I'm thinking about this is on top, that's the number of ways I can win. And on the bottom are all of the ways that something could happen. So that's 2 to the 10th. We calculated that here above for what happens with 10 flips, why the denominator is 10. And so here, this is equal to the number of ways to get one head divided by the number of ways the game can occur. And the number of ways to get one head in 10 flips, there's 10 ways. You could get a head on the first flip, or a head on the second flip, or the third, or the fourth, or the fifth. There's 10 positions where you might have gotten the one head that you got. So that's where that 10 comes from. And so here, the probability of x equals 5 should be the number of ways to get 5 heads divided by number of ways the game can occur, or the number of outcomes of the game. I'll put it that way. The question is how to calculate that. So right now, I'm motivating how to actually calculate the height of each of these bars. We did the easy ones. In this case, the easy ones were the small ones. So we already have the probability for x equals 0, which is equal to the probability that x equals 10, because the probability of getting all tails is equal to the probability of getting all heads for a fair coin. And we've also calculated the next easiest, because you can actually write it out with 8 ways. Well, at least you could see the pattern easily from the beginning. And yeah, we were able to calculate this. Just, it could be good practice for you. Taking this, the number of ways to get something divided by the outcomes of the game. How do you get 0.5? How do you get these two 0.5s from that same thing? I'll leave that for you as an exercise. We did it here for 3 flips and for 10 flips. This is really, what does the numerator mean and what does the denominator mean? And yeah, can you come out with what a numerator and a denominator would be for each of these? That's a good exercise to check your understanding. But for this, the number of ways to get 5 heads is the hard part. It's hard because you have to count. And people think that counting is easy, but counting can actually be very difficult. We know this, the number of outcomes of the game is 2 to the 10. Because I'm flipping a coin 10 times and I have a binary outcome that can happen. It's important to think about that and to become comfortable with it. It's natural for people to just kind of start throwing out numbers, or this feels right, or whatever. But even when it feels right, take a moment to pause and try to justify it to yourself. Do some simple check. Here, the number of outcomes of the game, thinking about the number of outcomes of 1 flip is 2. The number of outcomes for 2 flips, well, there's 4 outcomes. For 3 flips, that's 8. And now you've already got that it's 2 to the power of whatever you're at. Yeah, pause and take, 30 seconds or whatever it is to think through if where this thing is coming from. Okay, so anyway, this bottom part, the number of outcomes of the game, that's easier. This part, the number of ways to get 5 heads, is a little bit more difficult. So more space. I'm going to put this at the end, because we will end lecture with that. I'll give another break at, I don't know, 5:10 or something for like 10 minutes. I'll say that if anybody can come up with the answer to this question, should you play this game to make money? And can give a concrete answer, like, yes, you should, because of some specific reason, or no, you're going to lose money if you play this game, and here's why. If you play this game so many times, you'll lose this much money. Or, yeah, play the game. Yep, you can make money. In fact, if you play that game 10 times, you could expect to maybe earn this much money. Whatever it is. Yeah, the first person who can, after break, if you can walk me through your solution, I'll give you like an extra 1% extra credit on your final grade, something like that. So I'll try to leave this on the screen during our break. But before that, I want to take 20 minutes to talk more about this, counting. counting. So the reason why people care to count things, I hope, is obvious, because people care about what the, the count of things are. That being said, there's different ways to think about counting when in different circumstances. As an example, let me do this. Because I spent time drawing it, I'll just copy it. No, I'll do a different example. I like the picture, but I have a better example. No, I don't like that. Make it easier. All right, when I said that there's different ways of counting, I'm going to give a few examples. Yeah. Put this down for now. Okay, I want to pick on somebody. How about Asher? Hey, so here I have some 4 blue balls and 1 magenta ball. We'll call it a red ball. How many different ways can I have 4 blue balls and 1 red ball?
5 ways.
Why 5?
You can have the red ball in the first spot or the second spot or the third spot, the fourth or the fifth.
Great. Okay. So, okay. How about if you had 3 blue balls and 2 red balls?
$25.
25. Why 25?
I just took a guess and multiplied 5 by 5. Not really sure.
Okay, so
I know you could count it out and have like the red ball at the first spot and then move around the second ball.
yeah. Can you get so far as to say is 25 the right number or the wrong number?
I'm not sure.
Not sure. So you know that 25, I guess you got there by saying 5 times 5.
Yeah.
Right. Okay. So what is the first 5?
The problem, how many, there's one magenta ball in each spot? Or how many outcomes there are?
Right. Okay. So in your mind, I want you to picture 5 empty places. And in your arms, you're holding 3 blue balls and 2 red balls. Now, you're going to place the magenta balls first. How many choices, when you place the first magenta ball, how many choices do you have? Is my example making sense? It's not making sense. Okay, hold on. Let me do this. So here's a guy, and this guy has 1, 2, 3, 4, 5 balls. 3 blue, 2 magenta. And there's 5 places, right? So he can put the balls however he wants in these places. All of the different ways he can do it, that's what we're trying to count. Make sense?
Yeah.
Right. So when he was holding 1 magenta ball, you got the number 5 because there's 5 places for the 1 magenta ball, and after that, the rest are blue balls. So now that you have 2 magenta balls, keep placing the magenta balls. When you place the first magenta ball, how many choices do you have?
5.
5. Okay. Given that you have 4 balls left, right? And you've put 1 down. Now for the second magenta ball, how many choices do you have?
4.
4. Why 4? Why not 5?
Because one's taken away.
1 is taken away. Yeah. Okay. And so this is choices for first magenta, and this is choices for second magenta. And after you make those 2 choices, do you have any choice left of where the rest of the 3 blue go?
No.
Yeah, so that's it. So this is not 25. It's not 5 times 5. Instead, it's what?
20.
20. Yeah. Great. Yeah, and the reason why it's great. Okay, actually, that's it. Thank you so much. Thank you, Asher. So this is one type of counting where you can think about it as objects that have color, or objects that have a certain general property. Let me. Right. Okay, now I'm going to pick on somebody else. How about Ishan? Okay, no Sean. How about yeah.
Yep.
Hey, yeah.
Hi.
I want to know if you think if there's any differences between these two sets of 5 balls.
The order of the first 2 ball is different.
Very good. Okay, so if you look at their colors, they're the same. But if you number them, or if you have labels to them, then maybe the order matters. Do you agree?
Yeah.
Okay. So I'm going to ask you the same 2 questions as above. Question. How many ways for 1 red ball? And following that, Q2, how many ways for 2 red balls? And here I'll put order matters. Because you said that the 13 and the 42 are switched, so that matters to you to make these things different. Okay. Any ideas for the first question?
Mm,
You could use the same man holding balls picture if you like, or any other way you like to think about it.
so so I need to pick 1 ball from the first line and then from the second line, right? And then
Sorry. I'm just talking about having 5 balls. So you're saying
okay.
that these 2 sets of 5 balls are different. For example, these are 2 different ways that you could have 1 red ball. Right? This isn't 1 way, this is 2 ways. So, yeah, in total, how many ways are there?
There is there is 20 ways.
Okay, you say there's 20 ways. Where is the 20 coming from?
Because there are 5 balls and 4 of them can change their orders. No. Oh.
You said that because there's 5 balls and 4 of them can change their order. So you multiply these two numbers and that's where you get 20 from?
No. I think now they all can change.
Yeah. So if they all can change, does the color matter?
No, also the numbers matter. Other matter.
Oh, you say that the numbers matter, but the colors don't?
The colors and the numbers.
It could be. Yeah, you're right, that could be. If you had 2 balls with the same number, then you might think that they, yeah, maybe. But in this case, all of the numbers are different. So how many different ways can you order these 5 balls? If it's okay with you, I'm gonna draw this out a little bit. So, like before, you have balls, except now these have numbers on them. That's ball 13, that's ball 42, that's ball 18, that's ball 1, that's ball 5. Ball 1's a blue ball now. Okay, so this is your situation. You're holding these 5 balls. All of them have numbers on them. How many different ways can you place them down?
Sorry, can you repeat? I don't hear it very clearly.
Sure. So you have 5 balls, or 6. I'm sorry, yeah. So you have 5 balls, all of them numbered, and you have 5 empty slots where you can put them in any order you want. So how many different ways can you put the balls?
Maybe.
Think about the think about it one ball at a time. So you're holding 5. You're going to place the first ball down. How many places can you put the first ball down at?
5 places.
How many?
5.
5. All right. 5 choices for the first ball. Okay? And then, now you have 4 balls left.
Also 5
5?
choices each.
No. How do you have 5 choices for the second ball? You've already placed a ball. One of the places is taken up. Maybe-
So I just
Maybe you put
4.
a ball here. Okay? Yeah.
Mm.
Okay? I don't know, maybe put that ball here. So you have 3 balls left.
And 3 for the third ball.
Okay? Do you see a pattern yet?
Yeah.
Okay. So what's the pattern?
Yeah.
I'm asking
And
what.
then 2,
Okay.
1.
2, 1. This equals, you can also write it like this. It's called 5 factorial. So for this, it's 5 factorial, which is 20, 60, 120. 120 different ways you can do this. So as far as counting, there's different ways of thinking about it. And depending on the way that you think about it, you can get different answers. Here, order does not matter. So what it means that order doesn't matter is among the colors, we're ignoring the numbers. And then we can count one way. We can get a number counting when we ignore numbers. If we care about what the numbers are, then we get much bigger numbers. I'll just give this now, and maybe you can think about it. Oh, no, actually, that's another thing that I have to teach. Come to think of it. I'll leave this. We'll come back to that next class. In any case, I think this is good enough for today. The reason why I'm spending time talking about counting is because it's important for probability. When you want to count the number of ways to win, well, then there's a number of different ways I can get 5 heads. You know, I could get them all in the beginning, and then get all tails, or I could have 3 streaks and then a bunch of tails and then another heads and then a tails, and then I happen to get one at the end. And as you might imagine, there's a lot of these. They would be hard to write out by hand. Nobody would want to do that. So instead, you have to come up with a way to count them. And when you're counting, it depends on the game. Does order matter or does it not matter? And that's something that you need to be able to think through in order to come out with odds of winning money or losing money. Okay, so that being said, I want to give everybody a 10-minute break. Again, I'll leave this up. Is this game worth winning? Or is this game worth playing? Can you make money off of this? Or should you stay away because you'll lose money? I'll give anybody a chance to talk about it after break. But if nobody has a solution, I'll work through it quickly. All right, so let's take a 10-minute break. All right, welcome back, everybody. So yeah, today we're going to be ending the class on this example about whether or not you should play this game to make money. So does anybody think that they have an answer? Please type. Maybe I'm still working. I have a question. No idea. No time. Okay, well, then I'll just go through this really quickly. Is it worth playing this game? Oh, you have an idea. Mateo. Yeah, sure. What's your idea?
So my idea is that it's not worth playing this game because I came up with an expected value of getting 6 hits, sorry. And I got that by multiplying its rate of hitting the ball 0.6 times 10 swings. Or you could just do like each individual swing is a expected value of 0.6 hits, and then 10 times is six hits.
Mm-hmm. Yeah. Where X is 1 swing's average payout. No, 1 swing's. I'll just say where X is 1 swing. Okay. And so that's the expected is 6. And so then what?
So you would need 7 or more to make money, so it's not worth playing on average.
Okay. Okay. Good. Yeah. So this is correct. Fine. Yeah. So the logic is sound. Although there's one piece that I would like you to make explicit, which is about the payouts. Can you mention something about that?
So you would be expected on average to lose, you'd be expected to lose $50 basically if you play the game once.
No, that part I'm not so sure about. That part I'm not so sure about. Yeah. So, for example, you say that this is unfair, right? You should not play the game because what I was thinking is that the payout is the same. You could either win $50 or you could lose $50. And here, yeah, the expected number of hits is 6. And so the benefit is not equal to the chances of you winning. But what if I changed this? What if I said, you win $100 if you hit 7 times. You lose, you pay me 50. But if you win, I pay you 100. Does that make the game worth playing? Or still no?
Intuitively, yes, then it would be worth playing.
Mm-hmm.
I guess you would have to like calculate like the standard deviation to see how likely it is that it deviates from 6 hits. But with even like 50, win 50 or lose 50, you're going to lose money over time, is what I meant.
Yes, on that part you're correct. But yeah, that's sort of, yeah, you're right. That's sort of your intuition working in this example. But if I wanted to say, okay, so you say 50-50, win 50, lose 50, it's not a good game to play. Win 100, lose 50, okay. So then if I were to ask, like, what's the break-even point? At which point is it more worth it to play the game than not to play the game? Do you think you could find out what that number is?
Not off the top of my head right now, I couldn't, but
okay, yeah. So you have a really good start here. What I want to know is what is the expected payout? In the original question. The expected payout or loss. It'll be a payout if it's a positive number. It'll be a loss if it's a negative number. Here, you're saying that you should not play the game because you'll lose money. If you play the game over and over and over, you'll lose money more often than you make money. So
yes.
Stay away from the game. What I want to know is, how much money would you expect to lose playing this many, many times? So each time you play, maybe, yeah, you might on average lose $10. Or you might, for example, like you win some, you lose some, but on average you'll be losing this much money. So this is going to be an expected value. How would you begin trying to answer this?
I would use like the same type of math we did with getting 3 heads on 10 flips. Like doing the probability that there would be 1 hit, or it will start with 0 hits, then 1 hit, then 2, 3, 4, 5, 6, 7, 8, 9, 10. And then multiply, like, if it's 6 or less, the probability by, I mean, I guess you're multiplying it by 50 regardless, because you either win 50 or lose 50. You would multiply the probabilities by 50, basically.
All right. So this would be the expected payout per hit. And so you're saying calculate the amount of money that you would get for example, 0 hits. And that's going to be some amount of money. And then you multiply that by the probability of getting 0 hits, or the guy getting 0 hits.
Well, wouldn't you just multiply by 50?
Yeah, so you're right. So this is actually minus 50,
Yeah,
right? Because you lose money.
right.
And then this would be minus 50 times the probability of 1 hit. All the way until you're making money. The probability of 10 hits. Yes, this would get you the number. The hard part here is calculating the probabilities. But I don't want to keep people too long. So I won't finish calculating this, but just to get things started, because this is almost done, what would be the probability of 0 hits?
It would be 1 over 0.4 to the 10th.
One over 0.4 to the 10th. Okay, where are these coming from? Why is it 0.4 to the 10th?
Oh no, it would just be 0.4 to the 10th.
Yeah, I think it's just 0.4 to the 10th. Yeah. So that's the probability of the probability of not hitting is 0.4 because the probability of hitting is 0.6. So each time the probability of not hitting is 0.4. And then he doesn't hit 10 times in a row. All right, and for this next one, so that's minus 50, plus minus 50. Okay, how about the probability of 1 hit? So this is actually easier because order doesn't matter here. That is to say, if he gets 2 hits, for example, it doesn't matter if he gets a hit on the first and the second, or if he gets a hit on the second or the second and the first. Like, there's no difference between the ordering of these.
So there would be 10 ways he could get 1 hit. So it would be like 10 over 0.6 to the 10th.
Here, I'll do it this way. Yeah, we're missing something here. Yeah, this choose function is coming up again. So there's a couple ways that you could calculate this. The way that you're approaching it is correct. That will get you the correct answer. Where this 10 comes in, I know I'm using this strange symbol here, 10 over 1 with in parentheses. That is a function I'll have to talk about next time. Because for this approach, it's the missing piece. But yeah, I don't want to keep people past class. The class is already long enough. So thank you, everybody. Thank you very much, Matteo, for starting us off on this. And good luck on your homework. And I will see you guys on Thursday. Oh, Olga, if you could stick around so I can talk to you really quickly about your computer. Yeah. All right. Thank you, everybody else.